Hello everyone, my name is Brendan Schmidt, my partner is Sridhar and Nyshadham. Our topic for this video is hemodynamics of red blood cell deformability. Here is an outline for our presentation. Capillaries are the vessels through which red blood cells, or RBCs, pass through. RBCs are about 8 microns in diameter. Capillaries are only about half the size and average only about 3 to 4 microns in diameter. That is why it is important for RBCs to have the ability to deform in order to get through these capillaries. If RBCs are unable to deform properly, rheological dysfunction and cardiovascular disease can occur. For example, a decrease in the deformability of RBCs can impede the transit of cells to the capillaries where these RBCs oxygenate tissues. The question is, how do we quantify the deformability of a cell in a microchannel? One study we read used the device on the right to help model cell deformability. It varies with an angle to model deformability at different conditions. You can calculate attributes like entrance times, velocity through the constricted path, and the elongation index. The cell is assumed to travel through this channel without touching the walls. Knowing the gap of the cell, the size of the gap between the wall and the cell is important to measure the Young's modulus, a measure of strain versus stress, or how deformable the cell is. Using the Navier-Stokes equation with the lubrication approximation, the gap can be found using the above equation as a function of void fraction, pressure gradient, which can be modeled using the Hagen-Poiseuille equation, the size of the channel, and the transit velocity of the cell. You can use the cell radius from the first equation and the second equation to find the Young's modulus. There are many applications of calculating cell deformability, including disease diagnosis, determining cell viability, and characterizing red blood cells plugged in microcirculation. It can also be used to characterize the cell wall. Measuring cell deformability can be used for disease diagnosis. The microfluidic device shown on the right separates malaria-infected cells from regular healthy red blood cells. In general, malaria cells are more stiff than healthy red blood cells. Due to the margination effect in the channel, infected RBCs migrated toward the vessel wall, while healthy RBCs stayed in the center. The authors report 75% recovery of early-stage infected RBCs and 90% recovery of late-stage infected RBCs. RBCs consist less than 20% in microcirculation. At very low shear rates, RBCs assemble and form aggregates in the capillaries. This aggregation can be used to detect diseases including diabetes and obesity, as well as hypertension and arteriosclerosis. The accumulation of RBCs is affected by several factors, including the volume of cells in the blood, hematocrit level, and shear rate. The 3 images on top represent captured frames of RBCs suspensions flowing at about 10 microliters per hour at different hematocrit levels. The 2 images on the bottom represent RBCs suspended at 10% hematocrit at different flow rates. Cell deformability can also determine the viability of stored RBCs. This study measured transit pressure required to force RBCs through a 1.5 micron constriction from different lengths of storage from 0 to 14 days. They found that interquartile pressure increased dramatically after 7 days in cold storage, and a greater percentage of RBCs didn't transit through the constriction at all. They determined that deformability decreased after days in cold storage and determined that microfluidic deformability analysis could be used to evaluate the viability of stored cells. Characterizing RBCs in microchannels can also simulate how RBCs act when plugged in microcirculation. This study investigated RBCs under a long load, meaning they was pushed using a syringe into the microfluid constriction for a long period of time. They observed that the color of the cells darkened and that the length got shorter and shorter. After a 5-minute load, the cells were found to have shrunk to about 15% of their initial length. RBCs can be used to characterize the wall of the microvessels, specifically curved microvessels like capillaries. However, the curved shape of these vessels can play critical roles in the development of diseases. As an example, the curved shape of the aortic arch in the heart enables the blood ejected from the heart to reverse and move toward the body. This can affect the forces acting on the inner lining of the vessels and could lead to arterial diseases. The study focused on red blood cell deformation and the associated flow pattern in curved microvessels of various natures, which can be shown on the image in the slide. It was found that fluid close to the inner wall flows faster than fluid close to the outer wall. To conclude, RBC deformability is important to the health of an individual. This deformability is an important marker for rheological diseases. If a cell is unable to deform and make it through a capillary, blockages can occur in the form of aggregates, which can cause hypertension or diabetes, among others. In addition, applications of cell deformability include cell viability and disease detection.